Alright, so first of all, let me retract something about the condition variables. Totally slipped my mind here. The condition variables actually have one more feature that makes them a lot more difficult than we've considered, than we've discussed so far. A condition variable actually is able to release a mutex at the same time. When you wait for a condition variable, you pass a mutex in and it releases that mutex for a while, atomically, until the condition happens. So we're going to have to save that discussion for maybe next time or time after that, because it's a whole different chapter there. That doesn't change anything for our semaphores and barriers and mutexes, however, those are all as presented. So let's see. All right. There's also something about semaphores that we should discuss. So semaphores depend on the OS scheduler, right? So you're not spinning. You're not just running instructions checking some variable there. What happens when you wait for a semaphore, if it's 0, right? You call wait, is the scheduler, or there's a call to the OS. The OS decides, oh, this semaphore is 0. I'm just going to pause this whole application. So the program doesn't run anymore, and then it's put in a wait queue. That queue there actually suggests that we get some sort of ordering. All right? Whoever's first in the queue, when you notify later on, or when you signal this semaphore later on, whoever's first in the queue is going to get started. It's not like the OS is going to pick someone at random. But there remains the difficulty of knowing which one is in the queue. Right? Which one is first in the queue, because whenever they call wait, you could have two threads that call wait at virtually the same time, and we don't know which one's going to get in there first. So we can't use that much. We can't use that very much. This the fact that they are actually ordered. So they come out in the same order that they come in, but we don't know which order that is. Okay, so this is where we left off last time. We're trying to implement a barrier. Our barrier is actually working pretty well. Let's take just a brief recap here. So the barrier has some size. If enough threads wait on the barrier at the same time, then the barrier falls. You can go through and continue running. Right, so the way we implement this with semaphores is we have a binary mutex that protects the count. Right, so we have the n that says the size, and we have a count that goes up. If count equals n, then we signal that everyone can continue now. And either way, we wait. We wait and signal at the end. So what happens here? The first thread that comes through, it doesn't see count equals n, so it just waits. The second one, maybe not either, it just waits. Now the third, say you have a barrier of size 3, the third one comes in, it says, okay, 3, I'll just signal the other guys. One of them's going to start running, whoever came first, right? It's going to run through here. The third thread is going to be waiting. And then the second thread comes through, it signals, wakes up the third thread, which then signals again. Who does it signal? Nobody really. There isn't anyone there. So now our semaphore, our delay semaphore here has one too many. Right? Because we got 3 waits and we got 4 signals. So the semaphore is, the delay semaphore is 1 up. That's no good. Well, depends. So if we're going to throw away this barrier after this, we're not going to use it again, everything's fine. It's a perfectly fine barrier, and we don't need this count equals 0. Now, what we tried to do in a rush at the end of last class was try to make this barrier reusable. And so that's a bit of a different beast. So there's 2 problems here. Well, the count does need to go to 0. That much is clear. But we also want our delay semaphore to go to 0. And then finally, if we're unlucky, we might have a thread go through all of this and then go back in before we're done. Right? Before everyone has gone through here, the first thread might go through here, have some while loop outside, it calls wait again, and now it increases the count again. We might even lose this count, right? Because later on we set this to 0 in one of our other 2 threads. Right? So I suppose what happens then, your first thread sets it to 0, then come a couple more threads. They also try to set it to 0, but they kind of delay here. It's like first thread comes through, increments it, now it's 1 again, and then we set it to 0, so now we've lost the count. And all bets are off. So those are some of the problems we have to deal with here. Let's start with one of them. All right, so our delay here, it really needs to be 0. All right, at the very end. Oh, sorry, should it be 0? Yeah, exactly. It should be 0. It shouldn't be 1. So how do we fix that? We're gonna have to wait, right? The only way to increment or decrement is to either wait or signal, right? So we're gonna have to wait. But if I just say delay dot wait here, that's not really gonna work out. Right? Now we have a deadlock. Everyone's just gonna be sitting around waiting. So I suppose we first have to decrement the count to see, am I the last one? Right. If I am the last one, in that case, I'll wait. Okay, so let's try something. So we'll say if count equals 0, then we wait. Put it up. Let's see. Hey. Okay, so now the count goes down. If we're the last one, the count is going to be 0. Well, so before we leave, we just wait on the delay to bring that down to 0. What do you think?
What about the first problem, where another thread comes in? Like the first one is already done.
Yeah, that one we haven't dealt with yet. Let's say, for now, that they're all well behaved. They're only going to arrive, like the next wave of waits here is going to happen only after everyone's finished. Let's take it one step at a time. So would this solution work then? Yeah, we have one yes. Let's see, which one? There's 2 of them.
So when you have if count equals 0, so you're the last one and you call delay that wait, aren't you waiting for another signal?
Well, so what happened was I already signaled one time too many. Right? So if we forget about this one, you have 3 threads coming through. 3 of them are going to wait here. 3 of them are going to signal here, but 1 of them is also going to signal here. So we got 4 pluses and 3 minuses. We got to add 1 more minus. And so the only place we can do that is for the last one, I think. Yeah, I don't think it makes any sense otherwise. But at least it looks reasonable. Let's go with the last one. That's the extra way. Yeah.
Do it by chance need a mutex waits around outwards.
Right. You guys ought to be spotting this by now. We got a shared variable that we're accessing. Okay. So that was an easy one.
If it's not 0, do you want to
Let's see, if it's not 0, do we want to increment? Wait, which one is not?
If count is not 0, so we're not the last person,
Yeah.
don't we want to re-increment count because we decremented it? Or
Oh no, so the whole point here is when they come in, they all increment the count, so we know how many are in the barrier, and at the end they just want to empty out. So if we set it to 0 right away, then we have this problem, we don't know how many have left yet. So now we can keep track of how many are left, so you only do the delay wait once, right, for the last guy. Okay, just as an aside here, let's say I did this instead. Let's pretend we had another semaphore mutex 2 over here. Okay, we have a couple of people who know what's going on probably. Let's think about this one for a little bit. So, how many people think this would work, would not work? Okay. And how many think it will work just the same? Okay, so I guess the third alternative is, how many think it will work differently? Okay, so we have lots of abstentions and some people thinking it won't work. So why won't it work?
Well, because of locks, they could both be unlocked at the same time, so one could be incrementing while the other one is decreasing at the same time.
Exactly.
Yeah.
So we don't allow people to increment at the same time, right? But we allow one thread to increment while the other one is decrementing, because these locks, they are completely independent here. Okay, so we really ought to have the same one. All right. How about this? Again, the threads are well behaved. That when they come out here, they're just going to wait. They're going to do a lot of work. They're never going to come back in before everyone is out. Notice how we have maybe 10 lines of code here, and we keep staring at it. That's concurrent program. What? Was the count doing anything?
I mean, they have threads waiting on both sides of those counts. So as soon as it's a signal, it's going to increment and decrement right away.
Let's see. What am I missing here?
I think it's through. You have a thread waiting at the top and a thread waiting down at the bottom. Both of them. You take from the top, you take from the bottom. But both those counts, one's going to increment and decrement as a single thread.
Yeah, but they're not gonna. That's not gonna happen really. You can't get down here until n of them have gone past here, right? So we have n threads in total, presumably. That's why we put our barrier to n. And nothing's gonna happen. Everyone's waiting here until the last one shows up and signals, right? So this delay, it starts at 0. This is actually, it's called a turnstile. It's sort of an upside down lock, if you want. So when you have this wait first and then a signal on the same thing, what happens is everyone piles in there and just has to wait. So a turnstile is one of those, if you are not familiar with the term, let's see. I love Google Images. Here. It's one of these things. Right? So if this turnstile is locked, everyone just piles in there, right? And then, after you unlock it, they can go through one at a time, right? That's what's happening here as well. Here we have, this is the unlocking event. It's locked. When they first get here, the first few people, it's all locked. Eventually someone comes in and unlocks it. And now the first guy gets to go through, and once he's gone through, the next one gets to go, right? So you could imagine doing something in between here as well. Now you have a nice little serial phase here where only one thread at a time can operate in here, inside of the turnstile, if you want. Yeah.
Yes. So back to the mutex2 case, because if we have n threads already waiting a delay that, no, we have n minus 1 threads waiting a delay that way, right?
You're right, you're right.
So
It'll work just fine.
this should have been just working just fine.
Yep, yep.
So you were tricking us.
No, I didn't realize.
Okay.
Yeah. So this actually would have worked just fine in the non-reusable barrier case. Because you never have anyone trying to increment at the same time as someone's trying to decrement. It just can't happen. Everyone's waiting here until everyone's passed here. Okay, very good. Very good and very tricky business. Okay.
Sorry.
Yeah?
Would the comparison also need to be inside the mutex?
Ah, how come?
Because some thread could be decrementing it while you're trying to check.
You're right that it probably should be inside, but not because it could be decrementing it. When you're checking, you're going to get one of the two values, either the n or the n minus 1. So it's not like you're going to get some corrupted value. But what could happen is you could have all the threads go through here and then fall asleep right there. Right? So, you know, the scheduler decided that, oh, I need to run YouTube now. Right? I'm not running your homework anymore. We're going to do that YouTube video that's playing in the background. So now all these threads are just stopped right there, and then they wake up. Oh, and they all see count equals 0. Right? And so now they're all waiting, and we have a deadlock. So that's a good point. This needs to happen inside of the mutex. So now, only one of them gets to check at a time, right? So it's only possible for one of them to see count equals 0. Ah, yes. So this looked dangerous to me here. We gotta wait inside of the mutex. That's a recipe for deadlock usually. But we had one count too many. We already know. The only time this happens is when we have one count too many. So this will never block. So it's actually okay to do it there. Okay, so we're starting to get somewhere. Check my notes here. Okay, so we have one remaining problem. Now they're not well behaved anymore. Right? So now our threads, they have a little while loop, and sometimes they get very quickly from over here, they go back into another wait. In fact, your elevator solutions might very well be doing that too. Maybe you use the same barrier for both opening and closing the door. So now, one of the threads might not be quite done before we get around and go back out. So we gotta somehow make sure that the barrier is not admitting any new people until everyone's out. So this doesn't look quite like a regular turnstile anymore.
So the last thread can also set some int saying, oh, we're done. And then every other thread at the beginning, they do not proceed until the thread is not.
Okay, let's try that. We are done. Okay. So I suppose this starts out at 0?
Yeah, but it would have to be. Oh, yeah, sure.
So we're not done quite yet. Okay. So now we are done. So what do we check for up here? The first time around, we have to be done. I mean, otherwise we can't even get started. So I guess it has to start at 1. And then what? If we
can't grab this one.
Seems awfully hard.
The first one was like 7.
You know, an easier solution might be to do this turnstile thing again. But maybe we need something more like an airlock. You know how an airlock works? Like in a space station or something?
One door opens, you go in, door closes, you wait for something to finish, then the other door opens.
Yeah, exactly. So you have two doors, right? On the outside of one door is vacuum, and the outside on the other door is the space station. And in the middle, sometimes it's vacuum and sometimes it's air.
So another lock around the whole thing.
Another turnstile. So we basically want to have these people. They go into a room. So first you unlock the outside turnstile. Let them all go into the middle room. And you lock that turnstile. Unlock the other one. Have them walk out. And then when they all walked out, you lock the second one. Open the first one. All right. That should do it. So let's try that. What do we call this one? Oh, all done. Oh, let's see. Yeah, okay. So we'll say, the delay here is the second one. Really, so we want to block people from even getting into this count here.
So it's the same problem with an int.
What's that?
It's the same problem as with the int. If you had an int as a
Well, if you have an int, then you're going to have to wait, right? So you would have to spin, wait until it goes to all done, let's say. So, yeah, I suppose you could. With the semaphore, we have the advantage that we don't have to have that loop. It just the scheduler takes care of it for us. Okay, so one of them's gotta be, yeah, okay. All right. Okay, so let's just move this one in. I guess it doesn't matter if it's inside or out, but it really would be nice if it's inside. In this case, it might matter when we're done. Okay, so now we're saying let's see. So now we're unlocking the end. We're letting everyone out, right? And when we start letting everyone out, then we have to stop letting people in. All right, so are all done? Okay, maybe we say this is like welcome. All right, so they've been welcomed so far, but now we reached N. The room is full. We're not allowing anyone more in, so we'll say welcome dot wait. This is getting a little messy. Should I have some curly brackets maybe? All right, so now how does it go? Which one is in or out here, really? Oh no, let's. It should really be you may leave. So what we'll do is we have these threads coming in, and we don't let them just get all the way out until everyone's out. That seems easier. Okay, so no one may leave now. We start signaling that they can get through the delay, but they can't actually leave the second turnstile just yet. Okay, and then we're all done. So here, I say you may leave signal. And then it's the same story again, so we'll have over here, you may leave dot wait. Right, so here's the same turnstile again. So now we have a turnstile at the top that admits people into the room. Eventually, when there's enough people pushing on this barrier, they all get into the room. We go through here, and eventually, now we reach 0. So now everyone's waiting. Everyone except the last one is waiting over here to leave. Once the last one gets through here, now we've decremented to 0. Our delay is down to 0. Everything's the same. We've cleaned up this barrier. Now we let everyone out. Right?
There's still one problem with this.
Oh yeah?
Yeah, because we only care about the threads that actually came in and then leave and then want to come back up. But what about the threads that did not come in the first time, but they might actually come in, and then they increment our count?
Oh, I see. So we have n+1 threads.
Yeah, but our barrier should work for the interior.
It's unusual to have that kind of setup, where so barriers typically are there to say, oh, I have these n threads, I want them all to wait.
In our homework, we do that.
Yeah, in your homework, it's not like, well, I wouldn't suggest doing it with an unknown number of threads. I think what you want to do is have one barrier per elevator, probably. So now there's one passenger and one elevator competing. Or not competing, but going toward the barrier. I think if you have lots of passengers pounding on the door, and this can get very confusing.
But still.
So, okay, let's think about that. So, yeah, then we may, let's see. Yeah, then we have to have an entry barrier instead. An entry, let's see. How would we do that?
Before the count plus, we would have to stop.
Yeah, so we have to say, oh, when we come in, so we could probably maybe move this up here. I think that would work. So if we say, instead of you may leave, we say you may enter. And, oh, I don't know.
Could you maybe switch the count plus plus in the condition? So you check if it's equal to n first before you implement it?
Oh. What good is that going to do us?
Because then, if you're at n and nobody's entering, you can't implement it over n. So when you come back in,
that's true. But you know, there's more potential problems here. So you could have one thread leaving, and then that n+1 thread coming in, and now you're suddenly back at n again, right? I'll have to think about this one, but I don't think it's not typical to do barriers in this way, at least. I wonder if a pthreads barrier can do it sanely. Probably not. Maybe this will be a good homework. Okay. So we got a nice barrier, but that's one of many things that we need to deal with here. Let's think about something slightly different. So now we have a, let's see, Producer-consumer problem. Who's heard of the producer-consumer problem before? Well, you know producer-consumer kind of applications. We've done them. We've done piping before. So you have one thread that's producing stuff, or one process producing stuff. You have a pipe, you have a consumer getting stuff out of there. So the concern with a producer-consumer problem is the consumer shouldn't really be running until there's something to run on. All right? Let's see. And you could even have multiple, let's say in this case we do multiple consumers. So you have one producer, maybe it's Apache, right, the web server. Lots of requests are coming in. And the way Apache works is it has all these other processes, worker processes, that take something off of the work queue and executes, like returns a response. So Apache doesn't fork. Every time you get a request in, it doesn't fork, because forking takes a lot of resources and time, relatively speaking. So it has these worker processes doing the work. Same thing with creating a new thread. That would also take a lot of extra resources. Why does Apache not just use select instead? Why do we even want to deal with these processes and threads? Select is very responsive.
That we would only be doing one at a time.
Yeah, so if you want to run your web server on a multi-core machine, just using select is a bad idea, because all the other cores will just be sitting there idle, more or less idle. So if we want something to run quickly, you have to have multiple threads or processes on a multi-core machine. Okay, that was just like a little reminder there. So in the producer-consumer problem, we have a producer that fills up a buffer with work items, right? So for now, let's say buffer is unlimited. And we'll deal with the size a little bit later. Okay, and a consumer waits if there's nothing to do. Otherwise, removes one item and does the work. Okay? Pretty straightforward. So, what might be a good solution for this?
Conditional variable where we poke the consumer once we're done filling up the buffer.
We haven't talked about conditional variables yet, and we don't have any. We just have our semaphores here.
The counting semaphore would be in this case.
Yes, so we need to have, let's see. So we have two things going on here. First, we need to know how many items are in the buffer. And second, if we want to change the buffer, we need a some sort of mutual exclusion for that. So a conditional counting semaphore, that seems like a very good idea for seeing how many are in there. So let's start with that. So let's start with making the producer. All right. So the producer waits for some event. That's an incoming request, right? For So this is a while loop, but we'll ignore that. And then we have some mutex. Okay, let's declare a mutex. And then we have a buffer. I don't know what type the buffer is. Okay, so we'll say mutex wait, and then buffer dot add event mutex signal. Okay, so this is a decent start. So now at least we are able to add events nicely. Okay, so let's do the same thing for the consumer. Pretty straightforward. So now mutex.wait buffer.remove event. Oh. Okay, so far we are at least dealing consistently with the buffer here. We're not going to break the buffer. So I suppose we would like to know if the buffer is empty. If the buffer is empty, we can't remove anything. All right, so if buffer is empty, it's not empty. Actually, what do we say? While buffer is empty. Something like that. That seems like maybe that's a problem. Like, we want to wait for the buffer to have something in it, right? But if we do it here, the buffer will never have anything in it because we're locking the buffer here. So now we have the buffer locked, and we will never have anything in it. So we need a way for the consumer to wait without looping. We can't do it outside of here, right? If we wait like this, now the buffer might not be empty, and then when we get in here, now it's empty, right? Because there's multiple consumers potentially emptying this buffer out. Okay, so someone had a good suggestion. Counting semaphore. So what do we do?
I don't think that's necessary.
No?
No. Because consumer will only try to act once the producer is completely done, right?
Consumer doesn't know anything about this. Oh, you mean because of the mutex? Or what?
No, like they'll only start removing items once the producer is done adding items.
How is that?
Right?
As long as there's
Is that the scenario?
Oh no, so typically in a producer-consumer application, the producer just keeps running. Right?
Okay.
Keeps producing stuff, putting it in the buffer, and we just try to have our consumers finish it out every now and then. Right? So it doesn't grow to an infinitely large queue. So we want our consumers to wait until there's something to get.
So we could still be adding stuff to the buffer while removing stuff.
Yeah. But no, it's not going to happen exactly that time because we have these mutexes, right? So we're not screwing that part up.
If it's empty, could you just have a counting properly?
A counting what?
A counting semaphore, and just wait for the counting semaphore.
Okay.
And
Let's.
whenever they add something, just signal.
We call it count. And then what?
So whenever the producer adds something, signal the count, and then whenever the consumer. So if the buffer is empty, just wait for the count.
If the buffer is empty, wait for the count.
Yeah, and the consumer.
So how do we do that? We say if buffer is empty, count.wait.
Yes.
Well, we don't know if the buffer is empty because it could be empty now, but it's not empty once we get to the count of weight, right?
Also just do count.
Yeah, that's what semaphores are for. All right. So count, this semaphore is going to be 0. We have to initialize this. Start out at 0, start the mutex at 1. Alright, so when this starts running, count is 0. So the consumer is just going to sit there. And then producer comes in, signals count once, consumer starts running. And then producer maybe runs for a little while longer. Now we have hundreds of counts here. The producer then decides to take a break. Doesn't matter, you can run the consumer 100 times. And you can have multiple consumers doing it at the same time. Because you're only going to pass here if there is right now one more item for you. Right? And then you go and remove it. Yeah.
Do you have to put a lock on count that weight so they don't do consumers trying to like take the last item at the same time?
No, so that's the advantage of semaphores, right? That semaphores already do this in an atomic way. So the lock, if you remember correctly, remember the lock is actually a semaphore as well. So if that was the case, we'd have to put a lock around the lock. And of course one around that. Okay, so this is a very common thing, very common way of structuring an application. You have many cores, usually you have one deciding, like one master thread saying this is the work that needs to be done, and you have all these different cores, they're trying to fetch stuff from some work queue. So you'll run into this over and over. Now, you might get lucky enough to have a correctly implemented thread-safe queue, and then you don't have to deal with this. But if you are the one that needs to implement the correctly implemented thread-safe queue, then this will be good to know. Okay, so this brings us to the final, maybe the final, I don't know. No, certainly not the final, but the final one we'll do in lecture. I think the next homework will be a few problems like this. And we'll try to implement it using Linux semaphores. And then we'll have a barrage of test cases that you need to pass. Yes. So the next problem is a classic. The producer consumers, of course, that's a real classic. And so is the dining philosophers. This one here is another classic. It's called the writers problem. So it's almost the same thing. Who's heard of a read-write lock? Okay, we have 1.5.
In like SQL databases?
Oh, yeah. That would make sense. In fact, read-write locks are somewhat common all over. Let's think about mutual exclusion here. We have two threads, and they just want to check a count. They're not going to change it. They just want to check it. Do they need to be mutually excluded? So I have, like, if count equals 0, then do something nice, right? And I have two threads doing this. That's all they do. And there's no writer at the moment. There's no one changing the count. Should we have a mutex around this?
No.
We don't need a mutex because the count is never going to change anyway. So this is in general the case. If you have, even if there are writers involved here, if a reader, someone who's just checking, if they have the lock and you're a reader, there's no point in waiting, right? So maybe for tiny little things like this, it doesn't matter so much. But let's think about something slightly different. So you have this enormous graph, and now you want to query the shortest path through the graph. That's a reading operation, right? You traverse the graph, and you just look at the values of all the edges. Dijkstra's algorithm, for example. It's a reading problem, but it takes a long time to run. So, and then we have this writer on the side that every now and then decides to change the values of the edges. Maybe it's a traffic routing thing, and the highway suddenly got congested. The writer comes in and says, okay, it's red on the highway, so now everyone's going to go and route onto the side streets instead. So in this case, it doesn't make much sense to have only one thread be able to access this graph at a time. If you have these long-running readers, they really should be running at the same time. But your writer cannot run at the same time as the readers. You can't run Dijkstra's algorithm and change values on the edges halfway and hope for a correct result. It's going to be completely absurd. Okay, so we want mutual exclusion between readers and writers. No exclusion between readers and mutual exclusion between writers. Right, we saw this before. We've seen examples of this and this. If you have two I++s, it's you get a screwy result. And here, if you're checking a value at the same time as someone's changing it, well, it's not sure that after you check it, it still has the same value. So you may not be able to take an action consistently. Okay, but between readers, it doesn't actually matter. Okay, so that's our final problem here. We don't have enough time to look at the solution. There's some really interesting things happening here. Anyway, for the midterm, which is on Friday, someone asked, can we safely assume that, I'm interpreting now, that whatever's on midterm 2 was not supposed to be covered on midterm 1? I think that was the question. I don't know who posted it. So you, yeah. Was that the intent of the question? Yeah, so we want to know which exact chapters. So I'm not going to target a question at the chapters that were meant for midterm 1, but oftentimes you need to know what's going on in the previous chapters in order to understand the question even for midterm 2. So yeah, it goes a little bit both ways. But I'm not going to specifically ask a midterm 1 type question. File descriptor should be on. Yeah, I don't. Yeah.
From file descriptors.
Oh, and onward. Oh, I see.
Yeah.
Yeah, I don't have the book, but let me. Yeah, okay. I'll post something on Piazza. Let's see here what we have on the.
Give an example of maybe an application question that you could ask.
There might be something about latency, right? Differences between latency and bandwidth, perhaps. Might be something about TCP and UDP, like relative differences there. Probably some little, like I often have little like problem questions, right? Under these circumstances, why did things go this way? That sort of thing. Yeah, we don't have the time now, but okay, so let's see. Yeah, okay, so it looks like maybe 10.9 and on is I see. Looks like this is going to be mostly a networking midterm. Right, and then there was part of chapter 12. Right, so I'm sorry. I'm showing you the. I'm not showing the. Okay, so. Right, so it looks like here 10.9 was kind of the boundary. But I would certainly read chapter 10 again, review that with chapter 11, and then there was the beginning of chapter 12. So there's not going to be a linking question, right, on this midterm. All right, see you Friday.